Okay, so here's another problem where we're asked to find the slope and displacement at a particular point. In this case, it's the midpoint of the beam. And as we've talked before, this would be a challenging problem to do with direct integration, which is one of our techniques, but it should not be as challenging to do with conjugate beam. So I'm going to apply conjugate beam to this problem. So to do that, I need to draw the shear force and bending moment diagram for this beam. So I'll go ahead and assume positive shear forces at both sides. And then I'll find those values. So I'm going to sum the moments created by all the forces. I'll do it about B. No reason to do B or A, I just chose B. So about B, the 5 kip force creates what kind of moment? Positive or negative? Positive, right? And it has a moment arm of 3 feet. And then my reaction force over here, the shear at A, creates negative moment. And it has a moment arm of 12 feet. So it says the shear at A is positive. And I don't know what that is. What's 15 divided by 12? Is that 1.2 something? 1.2 what? 1.25. 1.25? And then if I sum forces in the y direction, I've got my shear at A acting up, my shear at B acting down, my 5 kip force acting down, and I find the shear at B is equal to what? Minus 3.75. Yeah.
Why did you assume B to be going backward?
Well, I wrote this as the shear at B. Remember, positive shear at B, positive shear on the right-hand side is down. Positive shear on the left-hand side is up. So I just wanted to go ahead and directly solve for my shear values. So these should be my values that when I draw my shear force and bending moment diagram, which I'm going to do right now, then I'll know where my shear starts and stops. Also, I'm going to mark this 5 kip load because I know my shear is going to have some changes there. So if I establish positive X and positive shear, then starting at A, my shear at A is 1.25. And we know that the change in shear is equal to the area in the load curve. The load curve is 0, so there is no change, so it stays 1.25. And that the slope is equal to the load, and the load is 0. Then as I go from the left to the right-hand side, I have a net change in my shear of negative 5, so that should bring me down to negative 3.75. Again, the change in shear is the area under the load curve, which is 0, so I'll stay. And that matches the value that I found. And the slope is equal to the load. The load is 0, so the 0 slope. So I have this constant zones of shear. Now we'll draw our moment diagram. Now we know in the moment that there's no moment at A and no moment at B. So I have a starting point and an end point. And we know the change in the moment diagram is the area of the shear diagram. This is a positive area. 1.25 times 9. What is that, 11.25? So I should end up here at 11.25. The slope of the line is given by the shear, and the shear is constant, and it's positive. So that gives me a nice linear curve for the moment. The change in moment over the last 3 feet is the area of this part of the shear diagram, which is negative 375 times 3, which I hope is 11.25 negative, which brings us to 0. That's great. And this curve is given by the shear, which is constant and negative slope, so we have a constant negative slope. So we get this triangular shaped moment diagram. And this will be kip feet. So let's start by drawing our conjugate beam. This one will not be that challenging, right? Because we know from our previous discussion that external pins and external rollers do what in the conjugate space? They're exactly the same. So I can just come over here and draw my beam, and the pin will stay a pin, and the roller will stay a roller. Okay? Now I'm going to apply this moment as load to my conjugate beam. And again, I'm just going to literally just copy over my moment diagram onto my conjugate beam. Now this moment is all positive. So load is what direction positive? Up or down? Up. So that means my loading on the conjugate beam is up. And it has a value here of 11.25 kip feet divided by EI. And these dimensions will be 9 feet and 3 feet. So we've converted our real problem into a conjugate beam equivalent, and now we're ready to proceed. So the original problem wants the slope and displacement at the midpoint, which is right about here, 6 feet from either side. So that means in the conjugate beam I need what at the midpoint? The shear and moment. So if you were to imagine this beam cut in half, 6 feet from each side, the question becomes, when I cut this, which free body you want to work with, the left side or the right side? Yeah, I think the left side here is a pretty easy choice. It's a simple triangle, whereas the right-hand side would be a trapezoidal segment and then another triangle. So we're going to go left. So I'll need to know the reaction here on that left side. So in that case, that would be, I'm assuming, the shear at A, and I would also draw my positive shear at B, but that's not going to be a problem because I'm not going to worry about that. Now to find this reaction, I'm going to need to know the total. So I'm going to first convert this triangular section. I'll call that F1, and I'll also have another force here for this one. I'll call that F2. So let's first find those forces. So what's F1? Well, it's 1/2 the base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. So what's that equal to? Let's see, that's I got 50.625. You guys get that? Anybody? No? Yeah? Yep. Okay, so I'm going to carry the decimal places right now too. So, and that's going to be kip feet squared over EI. And then the force for 2 is, again, it's a triangle, so 1/2 the base, which is 3, again times the height, 11.25 kip feet divided by EI. So it looks like it's just a third of the previous value, right? What you guys got? Oh, I got 16.875?
Yeah.
875, and that's kip feet squared. So not hard, but it's got to keep track of that. Now I'm going to find the shear at A, so I'm going to sum moments about B. So what's the distance from B to each of those forces? And I'll call those D1. So what's the distance to F1 from B? Well, it's 3 feet to this point, and then how much more? Yeah, a third of the base, which is 3 more feet, so that should give me a total of 6 feet. And then D2 is the distance from B to the centroid of this smaller segment, which should be 2/3 of the base, which is 2 feet. Everybody see that? So now, well, to get to this triangle, I have to go 3 feet, right?
Right.
And then the centroid distance of this one would be 1/3 the distance. 1/3 of 9 is 3. So I've got 3 feet here, and then 3 more feet. 6 feet total. So now I would sum the moments about B, make sure the whole thing is in equilibrium, and I just really need to keep track of F1 and F2 and then my shear force. So I'll start with F2. Both those forces are going to, in fact, all 3 forces are going to create negative moment about B. So I'm going to have 16,875 kip feet squared over EI, that's F2, times D2, which is 2 feet, minus 50.625 kip feet squared over EI, that's F1, times its distance, which is 6 feet, and then minus the shear at A times its moment arm, which is 12 feet. So I should be able to find the shear at A. It's actually going to come out to be negative. And what is that? That's a bunch of stuff there. Anybody else calculating this besides me? 28.125. Anybody else get that? You get that? Okay, so I got 28.125, and that's going to be kip feet squared divided by EI. And the negative sign just means that this reaction is down, negative shear, which makes sense. All the forces are up, so the reaction should be down. So now I'm going to come back, and like we talked previously, I'm going to look at a free body diagram to the left side. So let's see what that gives us. So that's going to be at 6 feet. My force is actually down 28.125 kip feet squared over EI. I've got this section of my triangular distributed load acting up. I'll come back to that in a second. And then I also have my positive shear force and my positive bending moment. And remember, the whole point of this problem is if I find this shear force at the midpoint in the conjugate beam, that will tell me the slope in the real beam. And the bending moment in this segment of the conjugate beam will tell me the displacement in the real beam. Now, one thing we have to figure out here is what's the intensity of that load right there. We know it's 11.25 here at 9 feet. What's it at 6 feet? Yeah, it's similar triangles. So this height is to 6, as 11.25 is to 9, which basically is 2/3 of that. What is that, 7.5? So this should now be 7.5 kip feet divided by EI. So any questions about that? So what I did is I did similar triangles. So see this triangle here? So I know it's 11.25 here to 9. So at 6 feet, what is it? So if you wanted to write it out, you would say whatever this value is, I'll just call it F. So F is to 6 feet as 11.25 is to 9. If you solve for F, you should get 7.5. I hope. So now I'll come back and find this force value. Let's call that F3. So I'll come down here and say, well, F3 is 1/2 the base, which is 6 feet, times the height, which is 7.5 kip feet, divided by EI, which is 22.5. You guys get that? That's 22.5 kip feet divided by EI. So I should have all the information I need now to solve for the shear and moment here. Let's do the shear first. That one should be pretty easy. So let's sum forces in the y direction. Is that equal to 0? So, yeah. Oh, sorry about that. Let me see if I can zoom out a little bit. That's kind of the same thing. How's that? Sorry about that. I didn't set it in there very well. So we're starting here. I've got my shear force acting down. I've got F3 acting up, which is 22.5 kip feet divided by EI. Oh, I made a mistake. This is kip feet squared. And then I have my reaction going down, which is minus 28.125 kip feet squared over EI. So therefore, the shear is, it looks like it's going to be negative. And it will be 5.625. And that will be kip feet squared over EI. I can tell you right now, when you take that numerator and divide it by E and I, it's going to be very, very, very small. Right? I guess numerically, so we now know that the shear maps into the slope, which would be this value of 5.625 kip feet squared. Now I'm going to divide it by E and I. So E in this case is 30,000 kips per inch squared. I is, there it is, 800 inches to the fourth. And I'm going to have a conversion of 12 squared, or 144 inches squared per foot squared. I have a feeling that's going to be a pretty small value.
Yep.
I got a bunch of zeros and a 3.
I got 3.38 times 10 to the negative.
You got 3.38? Yeah, my decimal place ran out, but that'll be times 10 to the minus 5.
Yep.
And that's radians. That's pretty small. Oh, and I also left out my minus sign got lost, so it is negative. Sorry, I'm kind of jamming all that in there.
So when you're actually doing like structural analysis of a real building, and you see the displacement's going to be like that, is that significant to use an engineer to see if displacement's going to
Well, small displacements and small rotations is an indication that you're still in a linear range, so that would be a good thing,
Okay.
typically. For this class, it really doesn't matter. I mean, it's good. I mean, if you'd have got a rotation there of, I don't know, 2 radians is a pretty big angle. Like a crazy big angle. Like your beam just spun around in a circle. So it has some logic to it.
Yeah.
But how do you measure 3.4 times 10 to the minus fifth radians? Can you even see that? It's pretty small, which kind of makes sense in the center, because your maximum point of displacement is probably just to the right here a little bit. So you might still be going down negative, and you're starting to flatten out. At some point, you'll go through a zero slope before you turn back up positive. So we're getting very near probably the point of maximum displacement.
Is the maximum displacement going to be 0 on the angle, the graph of the angle?
On the what?
Where the angle crosses the axis and goes to 0, is that going to be a maximum?
Yes. It has to be. Remember, one of our relationships was that. Let's see. The derivative of the displacement, right, is the slope. So we know if you want to maximize a function y, if you take the derivative and set it equal to 0, you'll find a max or min value. So that would mean the slope would be 0 at a max min. Which makes sense. Your shape has come down. It's flattened out 0 and gone back up, or your displacement's gone up, maxed out, and come back down. So it's a good spot. Some beams you may have multiple spots in a complicated structure where the displacement is maximum positive and maximum negative. Most of our beams, we don't have that situation. I'm going to try to squeeze this down in here in the bottom. I apologize for this, but let's see if we can do it anyway. So let's sum the moments at the cut and make sure that's in equilibrium. So looking at the moment, I've got the positive moment. F3 creates negative moment. So that's 22.5 kip feet squared over EI. That's F3. What's F3's moment arm from the cut? It should be 1/3 the total distance, and 1/3 of 6 is 2. And then I have my reaction over here creating positive moment, so that'll be plus 28.125 kip feet squared over EI, and that has a moment arm of the total length of 6. So I should be able to solve for the moment. It looks like the moment is going to be negative. Let's see what that will be. 123.75. Anybody get that? No?
Yeah.
123.75?
Yeah.
So I got 123.75, and that's going to be kip feet cubed over EI. So negative means, negative moment in the conjugate beam means what kind of displacement in the real beam? Up or down? Down. And that makes sense too. But you can see it's going to be a pretty small value. In fact, if I try to squeeze that in there, let's see if I can do this. Let's see if I can divide all that in there. So again, 30,000 kips per inch squared, 800 inches to the fourth. That's our moment of inertia. And then now the conversion factor for feet cubed is 12 cubed, which is 1728. And that's inches cubed per foot cubed. So all that will give me a displacement which I think will be really, really small. I got 0.0089. Did you guys get that? I'm going to have to write it here because I don't have enough room. I got negative 0.0089, and that's inches. Did you guys get that? Yeah, that's pretty small. Basically 9/1000ths of an inch. You'd be hard-pressed to even see that. Does that make sense? Well, this beam is only 12 feet long, relatively short. It only has a 5,000-pound load on it. Sounds like a lot, but that's really not much. This beam has a moment of inertia of 800 inches to the fourth. That's a pretty big section, and it's made of steel. So I'd expect very little movement. Probably you wouldn't be able to feel it. Well, I'll take that back. You probably feel the vibration of it as you walk across it a little bit. But really, you wouldn't be able to perceive it. I apologize for cramming this all in here at the bottom, but there it is. So any questions about that one? Okay.